I think we are just going to start now. My name is Guillermo Aldama, and I'll be chairing today's meeting. Today's meeting is an online only meeting. We will have some Q&A session at the end of the presentation. You will have on your screen, you should have an option to submit your questions. So please do that anytime that you have a question, and I will be reading the questions at the end. So for John to address them. Um, because it's an online meeting only, we don't have any health and safety announcements. So just please sit comfortable and enjoy the presentation. Today, it's my pleasure to introduce Dr. John Douglas. He obtained his PhD in civil and environmental engineering in 2001, following BSSC with honors in mathematics, both from Imperial College in London. In 2010, he was awarded his accreditation to supervise research in seismology by the University of Grenoble. He is currently a senior lecturer at the University of Strathclyde in Glasgow, working on the field of seismic hazard and risk evaluation. Previously, he was a senior engineer seismologist at BRGM in France. This is the equivalent to the British Geological Survey. And he, from 2009 and 2014, he was visiting professor at the Earthquake Engineering Research Centers at University of Iceland. Currently, he has an industrial fellowship of the Royal Academy of Engineering, and is working in collaboration with the Seismic Hazard Group in Jacobs on the development of a new ground motion attenuation model for the UK, which is going to be the topic of today's presentation. So without taking more time, I would like to welcome Dr. John Douglas to give us today's presentation.
Okay, thanks, Guillermo. I'm just going to share my screen. Can you see that okay? And can you hear me okay?
I can hear you and I can see you fine.
Okay, so you can see the slides, yeah?
Correct.
Okay, so welcome everybody. Thanks for joining today. So as Guillermo said, I'm going to talk today about the development of a new ground motion model for the UK. So this project is funded by the Royal Academy of Engineering through an industrial fellowship, and Jacobs are co-sponsoring this work, providing some money for expenses and in-kind staff time. So I'm just going to briefly go through an introduction, and then I'm going to get onto the main topic of today's talk. And then at the end, we're going to have a chance for some feedback on the plan for this project. So the project began in September last year, and it will run for 1 year. And so we haven't really got any results to show at the moment, but we're using this opportunity to get some feedback on the plan for the project. So the Royal Academy of Engineering are providing funding to cover my teaching for this year. And Jacobs, as I mentioned, are funding the expenses and in-kind staff time. So thanks very much for that funding. So the research aim of the fellowship is to develop a ground motion model for elastic response spectra for the horizontal component of earthquake ground motions for the UK, particularly focusing on the larger earthquakes, so magnitudes above 4. The fellowship has a more general aim as well, which is to increase collaboration between Strathclyde and Jacobs in the fields of teaching and research. So those of you who either work at a UK university or a UK employer might be interested in looking at these industrial fellowships for the future. I recommend it as a good scheme to get collaboration between industry and academia. The fellowships can go in both directions, either into universities or out of universities. Okay, so as I know some of you might not be completely familiar with engineering seismology, I'm going to have a couple of slides, just introduction to ground motion modeling, and then I'm going to get into the more the more focused part of the project. So ground motion prediction equations, or ground motion models, in the past they used to be known as attenuation relationships, but we've moved on from that terminology nowadays. Are simply a mathematical expression to enable the prediction of the median ground motions from earthquakes of engineering significance. So they are in the form such as this often. So this is the well-known, well, particularly in the UK, PML 1982 equation, which has been often used in the past for nuclear projects in the UK. So they express a measure of the ground motion, so in this case, peak ground acceleration, as a function of magnitude and the distance from the earthquake to the site of interest. And in the classic approach for empirical ground motion prediction equations, you take a database of strong motion records and you fit this model to the data and obtain certain regression coefficients, which are given here for this equation. So this enables you, this equation then enables you to make predictions of the earthquake ground motions, which could be expected from different size earthquakes at different distances. And you can have a graph such as this for this equation, showing how earthquake ground motions vary with magnitude and distance. So there's two further parts to this that I want to explain before moving on further. So one of them is the fact that if you have a set of data, so here we're just showing data from the Northridge 1994 earthquake in California, just for sake of an example, you can fit, so each of these points, these triangles, squares, etc., is a observation of the peak ground acceleration from that earthquake at a strong motion station. You can fit various curves through these data, each of which is potentially is equally likely to be the correct model of the median ground motions from this earthquake. So this indicates there's what's called epistemic uncertainty in the median ground motion model. There's also another aspect to this. If you compute the residuals with respect to any of these curves, so the colored curves in this case, you can get some residuals such as this. So this shows you how each of the points is differs from the median curve. So this is an aspect of, this is showing the aleatory variability or the scatter around the median. So in often in seismic hazard assessments, we account for epistemic uncertainty in the median through logic trees. I'm going to go on to what they are in the next slide. And the aleatory variability we account for model through the standard deviation of the GMPEs, often assuming a log normal distribution. So logic trees are a way to capture epistemic uncertainty. So often in seismic hazard assessments, when we're developing the ground motion model, we look at literature to see what models are available for our location. We use then some judgment to decide on which models could be appropriate for our study. Then, if available for the region, we might do some testing to see how well the models or the GMPEs fit the observations. And then we finally select a handful of GMPEs. So this is the classic way of doing seismic hazard assessment in the past. I'm going to go on to how it's changed in the future shortly. And then those models, you then maybe assign a certain weight to them depending on how much you think they're an appropriate model for the site and the region of interest. So just to show an example here, if this is from the SHARE project, which finished over 10 years ago now, a European project assessing seismic hazard around Europe. And for that project, we assigned different weights to 4 different GMPEs. The next thing I want to talk about, just before I get onto the discussion of the project, is what's called stochastic model. So you'll hear this phrase from me a number of times. So stochastic models is another way of doing ground motion modeling. So rather than use the data directly to derive empirical models, you derive what are called stochastic models by computing certain seismological parameters, so the listed here, on how the source, to characterize the earthquake source for your region, the path from the source to the site, and then the site itself. And then we use that to assess the Fourier amplitude spectrum, so that's shown at the top. And then we can then fit white noise to that Fourier amplitude spectrum and apply a window in the time domain to actually generate stochastic time series, which can be fit within a empirical model, within a stochastic model. So often this has been done in the past using the SMSIM software produced by Dave Bohr, and that's the software we're going to be using within this project. So now getting on to specifically for the UK. So the UK, for those of you who don't know the seismicity, is not well known for its earthquakes. There are some earthquakes that occur every so often, generally small and not damaging, but any nuclear power plant or critical infrastructure in the UK has to be designed against earthquakes. So there's been a number of studies being conducted over the last decades, and often these use, until recently, the PML series of equations. But these studies often neglected the epistemic uncertainty, either using only a single ground motion model or potentially only a couple, and hence that epistemic uncertainty was neglected. The stochastic method has been employed because we don't have much strong motion data for the UK by a number of studies which are mentioned on this slide. And then in the last decade or so, there's been a series of projects using the multiple GMPE approach mentioned earlier for seismic hazard assessments of sites at Hinkley Point C, Sizewell C, and Wilver, and a number of others. And then, so the UK site conditions are then captured within these logic trees using what are called VS kappa adjustments to adjust estimate the ground motions at the bedrock horizon of interest. So why do we need a new ground motion model for the UK? Well, there are a number of reasons which I'm going to go through on the next couple of slides. So one of them is the fact that the stochastic models that have been generated for the UK and used are poorly constrained for larger magnitudes and closer distances, which is exactly where we need reliable predictions of strong ground motions. The uncertainty in the UK decay rate, so the geometric and anelastic attenuation, has often not been completely captured by those stochastic models. And recently, in the last decade or so, the multiple GMPE approach has been shown to be problematic. So a number of reasons for that. One of them is the fact that the epistemic uncertainty that's captured using the multiple GMPE approach is not controlled by design by the ground motion modelers, but it's a consequence of which GMPs are chosen and the weights assigned to them. So you can get some perhaps non-optimum results from that approach. It's also sometimes difficult to then adjust the the ground motion model to a particular site conditions, because you need to know the host VS profile. It's also perhaps difficult sometimes to apply what's called the one-step site response approach within these multiple GMP approach as well. So on the first topic, which is particularly of interest, is the graph shown on the right-hand side show an aspect of this problem. So if you focus on the top left-hand graph contour plot, so this is SZCGMM, so that's Sizewell C ground motion model, you can see that the lower uncertainty is in the sort of moderate to large magnitudes at reasonably close distances, which is where we don't really have much data for the UK. So this could be suggested not to be an optimum ground motion model and capturing perhaps sufficient epistemic uncertainty at those magnitude distance ranges. At larger distances and smaller magnitudes, the uncertainty is larger, which again is maybe slightly contradictory to where we have the data. So we're trying to resolve some of these issues through this project. One of the approaches which has been suggested to perhaps try to overcome this is the so-called backbone approach, which I'm going to introduce on the next slide. And this is becoming standard for nuclear projects in particular around the world. So what are backbone models? So if we consider a single predictions from a single magnitude at different distances, just for simplicity, and we're plotting here, say, PGA versus distance. So in the classic multiple GMPE approach, we select perhaps 3 GMPEs, and this would be our predictions for that magnitude and distance, that magnitude and all distances. As you can see in this example, they intersect at a certain magnitude and distance, and hence the epistemic uncertainty captured at that for that combination of parameters is very small, which may not be an appropriate model that we think is an appropriate model for that magnitude and distance. So in the backbone approach, in the simplest backbone approach, we select a single model, and then we scale that single model up and down by a certain factor. So that could be, in the simplest approach, a simple factor to scale it up and down. But in a more sophisticated approach, you could have a magnitude distance dependent factor. So within the industrial fellowship project, we're developing a backbone model, and I'm going to go into details on that in a minute. So the advantages of this are that we're being transparent over the level of uncertainty that our ground motion model is implying, and we're rather than just letting the GMPEs handle it by sort of choice of the GMPEs. It means that there's a clearer meaning of the weights of the assigned to the different branches, because the branches are mutually exclusive and collectively exhaustive. And it's also easier then to make the model also site specific, because you don't have to adjust a suite of multiple GMPEs. So now onto the plan for the project. So I'm going to next 6 or 7 slides just show the plan of the projects in various aspects. So we're going to use the hybrid empirical stochastic method developed about 20 years ago by Ken Campbell, and it's commonly referred to as HEM. So when you see that abbreviation, that's what I mean. So in this approach, you have an empirical model for the host region. So this is not the UK. So this is a region where we have robust empirical models. So often places like California, maybe Italy, Japan, etc., where there's lots of data and well-constrained empirical models. Then there's an inversion to develop a stochastic model that fits that empirical model. Then in the UK space, we then look at ground motion data from the UK, and also we're going to be based using literature on what's been done in the past, what the various stochastic parameters should be. Using some inversion and judgment, we're then going to develop a suite of stochastic models for the target region. So this is the UK in this case. Then we combine the stochastic and empirical models for the host region and the stochastic model for the target region to generate a pseudo-empirical model for the target region. So this has the advantage of then borrowing aspects of the empirical model which we think are reliable. So, for example, how the ground motions scale at close distances and larger magnitudes where we don't have really any data from the UK. But it also borrows from the stochastic model for the target region to give a UK aspect to this model. And then in the last stage, we're going to then test the model against data, look at the implications in terms of seismic hazard for some representative sites, and then disseminate the model. So now I'm going to talk in the next slides about each of these boxes from this slide. So first of all, onto the host models. So we're going to use in the first instance the Chu and Young's 2014 empirical model. So it's been recommended recently in a number of studies, and it's also been adjusted for other regions. So we've got there's a good track record of the use of this model. And it's been shown to be very appropriate for the HEM as the scaling in terms of magnitude distance was carefully considered when it was being developed. And we're going to benefit from the work done by Stafford et al. In published last year, 2022, who provided inverted stochastic models for this empirical model. So now moving on to the target stochastic model. So these are the stochastic models for the UK. So this is really the key task within the project. And we're going to leverage the information that's already in the literature on the appropriate stochastic models and parameters. So I've listed a number of the relevant references here. And we're going to use those references plus some analysis of the available data to propose a suite of models capturing the epistemic uncertainty in these in defining the stochastic parameters. And we're also going to have to be careful with the parameter trade-off. So any of you who know the stochastic method, a number of the parameters, stress drop, kappa, geometric spreading, etc., all trade off against each other. So we need to be careful with how we develop those models to reduce the problems that we could get from the trade-offs. And then we'll parameterize those target stochastic models using the SMSIM software. And then for the host to target adjustment, so this is how you combine the empirical and stochastic models for the host region and the target stochastic models together. We're going to, we're planning to use the cheap software, which I developed with Hilmar Bungum and Frank Scherbaum almost 20 years ago now, because that implements the HEM approach. So for that, the Chu and Young's model has been added to that software. Cheap currently cannot implement the Stafford et al. Parameterization, the stochastic model, because Cheap uses a very old version of SMSIM. But we've come up with a workaround for that, so we can actually implement it within this project. There's a couple of open challenges. The first one I'm going to go into more detail in a minute. The other one is not really a particular challenge. It's just implementing the PGV model within CHEAP. That shouldn't be too difficult to implement. And then moving on to the testing. So this is another key aspect of the project. So we're going to we're going to look at the epistemic uncertainty that's implied by the developed ground motion model and compare it with the uncertainty captured in similar models for around the world and where we have data, etc., to look to see whether that's a realistic estimate of the epistemic uncertainty. We're going to also obviously compare the model to UK ground motion data, including any data that's been recorded in the last couple of years since the data collection was stopped. We're going to compare the model to intensity data points once we've converted it into macroseismic intensity. We're considering maybe using the ML models, so the local magnitude calibration models, to help check the attenuation rate of the ground motion model to see if it's realistic. And then perhaps we might also study the sensitivity of the approach to the host model. So perhaps switching out the Chu and Young's model and applying a different model as the host to see what effect that has. Another thing we're going to do is look at the implications of the model for UK hazard. So as I mentioned, we'll compute the hazard for a number of example sites and compare that to the results obtained using previous ground motion models for the UK. In terms of the hazard curve, the fractals, perhaps the UHS, and maybe the disaggregation of the hazard as well, to see how much of a change this new model would have if implemented in practice. And then the final aspect of the project is dissemination. So we're planning probably 2 open access journal articles. One on the model development, where we provide our arguments for the various steps and how we went about developing the model. And that's where we'll provide the coefficient files so people can implement it in their own calculations. And then in a second companion article, we're planning to include the model testing and implications section. And then we'll provide various subroutines, so in Fortran, MATLAB, Python, so they can be integrated with OpenQuake. We've also submitted an abstract to the SECA conference coming up in September. So we'll just do some dissemination at that conference. And then if invited and SECED are interested, we can maybe perhaps give a final evening meeting sometime in maybe the autumn or the winter once the model has been completed. Okay, so that's the end of the first half of the talk. I'm now going to move on to discussion of challenges and some solutions. So there's at least 7 challenges which we've identified in the development of ground motion models for the UK. So a number of these are probably the same issue for other regions with low to moderate seismicity. And so I'm going to go through the challenge and then perhaps a partial solution to that challenge. So the first up is the fact that the depth range for the UK, for UK seismicity, is uncertain. So it seems that larger magnitudes occur between roughly 5 kilometers and 25 kilometers of depth. But there are a few earthquakes with reliable focal depths. Routine depth estimation relies on having a very dense seismic network. and hence the depths, the most reliable depths are for special studies. So it's been reported that the depth uncertainties could exceed plus or minus 10 kilometers for the UK. One interesting aspect of UK seismicity is shown on the bottom figure. So if you plot the focal depths versus magnitude for British earthquakes, the larger earthquakes seem to occur at larger depths. As you can see, the earthquakes larger than magnitude 5 seem to occur around 20 kilometers depth, and those for smaller magnitudes, perhaps the average is maybe 10 kilometers. So if this is true, this is quite an important aspect to capture within the ground motion model. One of the issues with that, though, is that the deeper earthquakes from the larger earthquakes have are from the before 1970, when the seismic network in the UK wasn't as well developed. Hence, a lot of these depths are from macroseismic observations. So we're not entirely sure whether those depths are reliable, and hence there's a bit of uncertainty there in that aspect. So the ground motion model, the depth plays a role in the calculations of the distances from the source to the site. Hence, we need to capture that potential dependency of focal depth on magnitude within the calculations of the model. So we're planning to develop a Z-TOR model. So this is the depth from the top of the rupture, the earthquake rupture, to the surface. So this is one of the parameters in the Chu and Young's 2014 model. So the uncertainty in that dependency will have to be captured through perhaps multiple Z-TOR models. The next challenge, which is and often a challenge in low to moderate seismicity, is the fact that we've got limited data from the larger magnitudes and closer distances. So if we look at the available data from Northwest Europe, so we're not limiting the data selection to the UK, but we're including parts of northern France, Belgium, and the Netherlands with similar tectonics. We can get the plot shown on the right hand side here, showing the magnitude distance of the ground motion records. As you can see, there's only a handful of records from larger earthquakes than magnitude 5 and closer distances than 50 kilometers. So this means it's difficult to assess magnitude scaling because we have quite a limited range of magnitudes in the data. And it's also difficult to determine the stochastic parameters reliably because there's of these trade-offs. However, the data does give us some handle on the attenuation with distance. So if you can see, there's a reasonably good data spread for the larger distances, and that can give us some handle on the geometric spreading and the Q parameter. So as alluded to earlier, the solution to this is we're going to propose a suite of stochastic models, not just a single model, which will account for the epistemic uncertainty in these various parameters. So the key ones being stress drop parameter, geometric spreading, anelastic path attenuation Q, and the site attenuation kappa. And then we're going to use expert judgment within the project team and data where applicable to weight the various stochastic models developed. And then it's important then to test the predictions from that resulting ground motion model against the data. And the final model will then have multiple branches, so not just a single backbone, but multiple branches from that backbone to capture the uncertainty in those various parameters. The next issue, which is slightly related to the last one, is the fact that there's because most of the data is from larger distances, smaller earthquakes, there's the signal to noise ratios below about 1 hertz and above about 10 hertz are often quite low in the data. So this means it's difficult to then estimate the stochastic parameters because you're trying to estimate them through the noise of the data. So an example is shown at the bottom where you can see that above on the right-hand side, the Fourier amplitude spectrum for this record shows that on the right-hand side, you can see perhaps above about 15 hertz, there isn't, there's basically the signal to noise ratio is 1, and you can't really use that data for estimating stochastic parameters. So a solution to this is similar to the last one, where we're going to propose this suite of stochastic models. And this maybe means that we can only test them within a narrow frequency window. And then outside that window, we'll expect higher uncertainties because we don't have the reliable estimates of the ground motion for very low frequencies and very high frequencies. The next issue is related to the metadata. So despite great efforts in the last decade or so to collect and report local site conditions at seismic stations in the UK and surrounding countries, it's still quite heterogeneous information that's available. So Sarah Tallett-Williams in her thesis and Villani et al. In a paper from 2019 provided some information on strong motion VS30s and site class information. But there's a number of sites where we don't really have very much information at all, apart from geological information about the site conditions. So this means that it's difficult to then adjust the data to a reference rock condition. And hence there's some uncertainty there in how to use the data. So the way we're planning to cope with this is to estimate a VS30 for every single station that we have data from. So this obviously is quite uncertain for some stations where there's little information, but we think that it's better to have an estimate despite a large uncertainty than not have any, not to do any adjustment or to not use those data. So, and then once we have a VS30 estimate, we're then proposing to use the site amplification function proposed by Bayliss and Abrahamson in 2018 for their Fourier amplitude spectrum ground motion prediction equation. So this then allows us to adjust the Fourier amplitude spectrum that was observed at the site and make it appear to have come from a specific reference VS30. So an example of the application of this approach is shown on the right-hand side here. So we have the original record from the OLDB station, and then this has got an estimated VS30 of 360 meters per second. So if we adjust it to a reference of 1000 meters per second, we get the curve, the time history shown at the bottom. So in this, what we've done is we've divided by the site amplification estimated based on those two VS30s. And it, as you can see, it then reduces the amplitudes as expected, because we're going from a softest soil to a rock conditions. So the next challenge is the fact that the VS profiles for the UK are poorly known in general. So what I mean by this is the fact that we have increasing amount of information at the top, perhaps 50, 100 meters at well-characterized sites. So for example, the nuclear power plant sites and so forth. And we have a number of good studies from seismological data for the crustal structure below about 2 kilometers from using tomography or other techniques. And between these, there's a poorly known zone where the information on the VS profiles, VS estimates in that region is quite poorly known. So this is shown in this figure here, showing a number of crustal structure and site-specific profiles. So the way over this is we're not trying to derive our model for a specific site. What we're trying to do is derive it for a representative generic UK profile, which will provide that profile, the VS profile, to the user. So then they can use it within methods such as the two-step approach or the one-step approach to adjust the provided ground motion model to their site-specific conditions. So the representative profile will be based on the information we have available, so that if it is applied without adjustment, it provides a good estimate of the rock ground motions for the UK. Obviously not for a specific site, but for a sort of generic site. So the next challenge, it's not strictly a challenge, it's more how best to use the macroseismic intensity data that we have. So macroseismic intensity data for the UK and surrounding regions is very abundant. There's been a long history of collecting that data and providing it. And often that data, because it goes back further in time, has a better magnitude distance distribution than the instrumental data. So we have more larger earthquakes, closer distances in that macroseismic database than we have from the instrumental record. However, correlating the ground motions, instrumental ground motions to macroseismic intensity is quite uncertain. And there's little co-located ground motion, instrumental ground motion intensity data for the UK in which to study the correlation between these two parameters. So how best to use these data? So we're going to use these data within testing phase. So converting the ground motion model from instrumental ground motion parameters to macroseismic intensity, and then compare that to the observed intensity from some important earthquakes. To account for the uncertainty, we can then use multiple ground motion to intensity conversion equations to capture that uncertainty. And we can also use the coefficients of intensity prediction equations, so those derived by Roger Musson and others for the UK, to inform the stochastic parameters that we include within our suite of target stochastic models. So for that, we're going to follow the approach used by Strasser et al. 2015 for South Africa, which is shown on the right-hand side. The final challenge is the development of the aleatory variability or sigma model. So our focus in the project is particularly on the median model and its epistemic uncertainty, but we obviously need to provide a aleatory variability model alongside that so that people can use it for seismic hazard assessment. So as mentioned a number of times, limited data means we can't really derive a UK specific model. And there's few stations with multiple records in which to study single station sigma for the UK. So the approach that we're planning to follow is to recommend one of the existing sigma models, so Chu and Young's itself, perhaps the El Altique 2015 model or others, but to then compare the observed variability in the ground motions against those sigma models to see whether what the observations show matches those models. If there's sufficient data and there's sufficient difference, we might propose some minor modifications to those models for the smaller magnitudes, perhaps greater distances in the UK. Obviously, we can't really suggest any changes at the larger magnitudes where we don't have data in which to base that on. So that's the 7 challenges and the plan. So the final part of this presentation is really asking for feedback from the audience. So we'd appreciate your views on the project plan, because what we want is the ground motion model we're developing at the moment to be as useful for the community as possible. And if you provide a request now, it might be possible to make some slight changes to our plan. If it's later, then it's obviously going to be difficult to implement it. I just want to, before people ask for very large changes to the plan, just to consider the constraints we have in terms of budget, time, and data. So we can't really do any more data collection. The budget and the time is limited by the fact we need to complete the project by September. So we're going to launch an online questionnaire at the end of this presentation, and we've got some questions to sort of launch a discussion now, and you can complete that questionnaire at your leisure later. The final request would be if anybody's interested in doing a late stage review of the model once everything's complete and the papers are written. That will probably be in August, more likely September time that we would ask for that review. So please let us know. So the questions which we have, which just to sort of launch the discussion, are these. So, would you likely use the model and for what applications? Do you have any concerns over the adoption of the hybrid empirical stochastic method for the UK? Are there any other inputs which we can use to constrain the UK target models? What should be the target VS profile for our model? Are there any other data or strategies for testing which you'd like to suggest? And then a catch-all, are there any other reasonable requests? And then finally, who's interested in being a late stage reviewer? So we've got, I think, probably about 20 minutes, 25 minutes to have this discussion online, but we can also, if you've got your phones ready or you want to make a note of the link shown here, we've set up an MS Forms, and that QR code should take you directly to the questionnaire, which is available online. And we'll have a look at I think we're going to put a deadline of maybe 2 weeks from today for comments, and then we'll have a look at those and see how we can maybe modify the approach if there's any particular issues we think you've raised which are very important. Okay, so just to thank you for that, I can put the QR code up again at the end, perhaps as we close the session. So I just want to thank everybody again for attending, and we'll be welcome for any comments or questions. Okay, if you want to email me directly, I've put my email address up there as well. Okay, thanks very much.
Thank you very much, John. Quite interesting presentation. I was thinking probably I might approach second committee, and we might be able to put the QR code as well on the second web page.
Okay.
So there might be, not promises, but there might be a chance to have that at least for a couple of weeks, just so people can access the second web page and then probably just access the questionnaire.
Would it be possible maybe to put the URL into the chat to the audience, or is there no chat to the audience?
Yes, I will have to
Wow.
try to
Good.
see that one. I don't know if you have access to the chat.
I don't think so, but
Guillermo, yes, you can reply in the chat.
You will have to just give me a second then, and I can.
Do you want to drop a message to
Yes,
all? Or,
a message to everybody.
I don't believe you can do that. Sorry.
Okay, so
anyway, we'll maybe have the discussions, and then I can put it up maybe at the end as we
yeah,
close. Okay. All
yeah,
right.
that could be an option. So we already have a number of questions. I'm just going to take them in the same order as they appear on the chat. So the first one is from Wei Wei Shan from the University of Texas at Austin. The question is, what types of evidence are used to assign the weights in logic trees for epistemic uncertainty?
It's quite a general question. Is that specifically for the UK or for in general? Well, for the UK, we've got the data which is invaluable in this case. We can use, if the data doesn't support one of the hypotheses, that might obviously get weighted down. We can also use perhaps analogues to other regions, so tectonically similar regions. So perhaps I'm thinking of France here is close by, where there's been a lot of work recently. We can perhaps use some of that information to help the weighting. We can use some physics-based arguments as well, how the scaling physics suggests the scaling should be. There's obviously a lot of expert judgment here. There's also the macroseismic intensity data, which can provide us some good evidence for the larger magnitudes, closer distances. Guillermo, do you have any other suggestions for that? It's a
Not
big
really, but
topic.
I was actually, I have a question for you because now that you mentioned the macroseismic, the advantage of having the macroseismic data is that is significantly more abundant than the instrumental data, and also there is more data at near source data, the closest distances. How much value you think that is going to add that on to characterize the attenuation of the ground motion with distance?
I think quite a lot, although there's obviously the uncertainty in the fact that we've got intensities are discrete values, so it can't be used in the same way as instrumental data, and also there's that uncertainty in the conversion. So I think it's going to be more as a qualitative evidence as opposed to a quantitative evidence. But the work done by Fleur and others in South Africa, I think, is very interesting in using that information to try to constrain those parameters.
Perfect. Let's move on to the next question. This is from Andrés Felipe Alonso Rodriguez from the Catholic University of the North. He's asking, taking into account the fact that you are assessing hazard for nuclear plants, do you have make particular provisions for pulse-like near-fault ground motions?
Not particularly, no. The UK ground earthquakes are, as I've mentioned, generally quite moderate earthquakes. So we're not really expecting that type of earthquake. The key scenarios for UK seismic hazard, even at 10,000 year return period, so 10 to the minus 4 annual frequency of exceedance, are sort of magnitude 5.56 at maybe 30, 50 kilometers. So we're not really expecting a pulse like near fault ground motions to control the design.
Okay. Moving on to the next one. This is from Sigelkowski from Marup. This is more like a comment and a request. It says, John, an excellent talk. I provide some thoughts to you offline. And he has one request. So can we please share this with key UK experts in the field who have not had the opportunity to listen to your excellent talk? I think I can comment on that request. This talk should be in about probably 2 weeks, become available online, both on the IEC webpage as well in the second YouTube channel. So it's going to become available for everybody. And then if you are aware of anyone that might be interested, probably just email John directly or put that person in contact with John. That will be very useful. Following question is from Fatemeh Soleiman from the I'm going to struggle pronouncing this. Kabir University of Technology. He's a PhD student, or she, I'm not sure. He says, thank you for your valuable information. Have you ever tried machine learning approach instead of linear regression models?
Personally, I've never done a machine learning model. There are a number in the literature, and they do have they're an interesting approach when you've got a lot of data. So because they allow you to then look at the characteristics of the magnitude distance scaling in much more detail than a classic linear regression model or a regression model. The problem is for the UK, we don't really have the data to do that. So it might be possible for sort of magnitudes 4 from 50 kilometers, but that's not really where we need the predictions. So I think there's debates over that machine learning approach for that sort of limits of the data. I see, and that there's a question by Boumediene Deras, who's done a lot of work on this in the chat there. So I would suggest having a look at his papers because he's done some nice work using the NGA West 2 database, machine learning, and there's a number of others in the literature. So it's a promising approach, but it doesn't solve all the issues, I think.
Thank you. An additional comment from Sigi Lukowski. He's saying, I can offer to put a link into the second social media accounts, assuming you're happy for it to go in the broader community. I think that's an excellent idea.
Yeah.
We'll get in touch, Sigi, to do that. And also, John, do you think there is also an opportunity to share the presentation online as well, so people can have access to the presentation as well as
I don't have
the
any issues
questionnaire
with that. Yeah, that's fine.
So in that case, people, because I was thinking if there is a delay of about 2 weeks to get the video online, there is some value on people going through the slides and looking at what is has been presented there, and probably just pick up the brain. That basically is the main objective of this presentation, to invite people to collaborate and to share ideas on the plans that we have. And well, yeah.
I thought, is there any other questions? Or otherwise, I thought I might just share that link again, the QR code, if people want to, if they do have any comments, à chaud, as they say in France, they might.
Those are all the comments so far, but I mean, the QR code is there. We can keep talking in the background. In the meantime, I actually have a question myself for you. You already mentioned that one of the objectives of the project is to test the different, let's call host GMPs to instead of using Chiu and Young's 2014, probably using an alternative model. My question would be, well, this Chu and Jones was developed for active regions, but in this case, we're adjusting that to a stable continental region or to the UK in specific. There are few well-known behaviors on the ground motion attenuation of stable continental regions, like the effect of this Moho boundary that present a plateau at certain distances. Do you think that might be an issue that should be something that might be solved when the stochastic models are developed and then doing the applying the HEM approach?
I think they should be accounted for by doing the adjustment using the stochastic model for the UK, as it's basically uses the ratio between the empirical stochastic and then the stochastic for the UK. So any change in the distance attenuation should be accounted for. When we did the study for Sizewell, that preliminary backbone that we did there, that obviously showed that Moho bounce because we used the Riprock and Edwards stochastic model. So I don't really see an issue with that. Although it would be interesting to see how stable the results are if we use a different host model. I think theoretically it shouldn't really have an effect, but it would be interesting to check that.
Thank you. I don't have more questions on the chat.
Does everybody know how to put questions in if they do?
Yes, there should be an option on your screen where says just send questions. So just give it 1 minute or two to see there are more interest. We have actually a good attendance. At some point, I got reported that we have 106 attendees. So
that's good.
A good attendee. Another question from Andreas Nielsen from Atkins. The title of the presentation contains the words "for engineering purposes." How do you see this work maturing to a point where engineers can use the outcomes? Will the outcome be an application that can provide a uniform hazard spectra at a specified confidence level and a specific return period at any point in the UK, assuming the reference VS30 profile, or how will the engineers be able to use the ground motion model?
Okay, so we're planning that the model will be used particularly in nuclear applications where there's a probabilistic seismic hazard assessment being conducted. So Jacobs hopefully going to use it at the end of the project for within their any of their projects in the UK. I don't really see there's a particular problem of using it. It'll be obviously a bit more complicated maybe to use than a classic multiple GMP approach, but we're going to provide the coefficients and the subroutines so that people can evaluate the ground motion model, well, the different branches of the ground motion model. So obviously it will make it a bit more complicated because the logic tree for the ground motion model will perhaps be a bit more branches than people would normally be used to. But I think it should be applicable. And then perhaps if BGS in the future update the UK seismic hazard map, perhaps they might consider this model as a appropriate one for that update. We're not planning to propose uniform hazard spectra for lots of different sites in the UK develop using this model. We're just going to select a few representative ones, and then it will be up to the users to do it for other locations. If there's any particular aspect which you think might make it difficult to apply, we'd be interested to hear that, Andreas. That would be interesting to hear.
Also, another thought from myself. Do you think it would be a good idea to provide a more simplified backbone model with less branches, just for more, I don't want to say simple, but more less complex PSHAs? Like, I don't know if there is something that is not with the level of rigor of the nuclear industry, so that they can still implement the model without having large number of branches.
Might be feasible. We're doing some pruning, you mean? So we need to be
Yes.
careful that we maintain the same level of uncertainty as the full model. Not something I'd thought about. Perhaps it's a good idea. We can maybe I'll make a note of that as something which could be applicable. We don't really know as yet how many branches we're going to have, but obviously if people are wanting to run the hazard for lots of sites, then fewer branches the better. Yeah, I'll make a note of that. Okay, thanks. Anything else? Did we finish at 1:15? Is that right?
Well, we have up to 1/2 so we have enough time. If you want to add anything else, I don't have any more questions on the chat.
I don't think so, but
well, probably one last one for me then. At some point you mentioned this model can be then used to in a PSHA, and then site response analysis, you can apply this one-step approach that is relatively new for the incorporation of the site response into the PSHA, or the traditional two-step approach of the additional host to target adjustment for specific sites. In that case, because this model has been adjusted to the UK conditions and you have the VS cap adjustments, do you see a need to use the single station sigma models, or probably the double counting of the site or the aleatory variability and the site response analysis of the epistemic uncertainty as well might have to be taken into account?
I think the single station sigma models will have to be used, and applying it for a specific site. I'm not sure the difference, why the one-step approach or the two-step approach would change things in that case. Could you explain it more? Or
no, I was not referring whether it will depends on whether you use the one-step or the two-step. In either case, because you already have, or we already have, some site-specific conditions, also to a genetic extent, a genetic VS profile, whether at some point there will be the need to consider the single station sigma.
I think they will be, yeah, for a site-specific study where we have we know the profile for that. If we don't know the profile, for a national seismic hazard study, I don't think the single station sigma should be used. But for one where we do have a profile and we're adjusting it to that specific profile, we should use the single station sigma. Yeah. I'm just making a note of the pruned idea.
Okay. Well, there are no more questions on the chat, so I think in that case, I would just like to say thank you very much for the presentation, John. Hopefully this project is going to be a success, and it's going to be of interest, and it's going to become a useful model for all practitioners in the UK, And well, we are not face to face to give you a round of applause, but thank you very much for sharing all this information with us.
So just before we close, about the circulating of the presentation, I can produce a PDF. What should I do with it? Should I provide it to you, Guillermo, or should I?
Yes, send it to me, and I get in touch with Sigi and
yeah,
with all the relevant information. I think the QR code can be easily uploaded to all the social media, SECA social media, and then add a link. We figure out, because I was thinking it will be easier to have it the PDFs somewhere in the cloud, and in social media just add the link to that to the presentation.
I mean, I could probably put it on our OneDrive, University OneDrive, and then send you the link.
Probably that would be I think that would be a good idea.
Okay, maybe I'll do that before I leave the office just now.
Okay.
Perfect. All right. I just want to thank everybody for joining again, and hope to see you in person sometime. Okay.
Thanks from my side as well. Thank you, everybody. Thanks for all the interesting questions, and have a good evening.
Yeah. Bye.
Bye.